Welcome to This Explainer. Today, we're undertaking a strictly formal, technical review of the Aurora theoretical framework. We'll be looking at a fundamental architectural shift in how artificial intelligence represents semantic meaning, specifically moving away from the probabilistic distributions that dominate current natural language processing and toward a model of ternary embeddings and recursive coherence logic. Our goal here is to impartially examine the mechanics, the mathematics, and the theoretical viability of this proposed system.
Our agenda for this analysis covers 6 core areas. First, the limits of probabilistic embeddings. Second, the Aurora architecture hypothesis. Then, ternary tensors and identity, followed by recursive logic and consolidation. Finally, we'll examine semantic mitosis in polysemy and close out with system advantages and theoretical constraints.
Let's begin with Section 1, the limits of probabilistic embeddings and the current statistical paradigm.
So there's a foundational divergence we need to establish right away between current systems and the Aurora framework. In the classical statistical paradigm, models process massive text corpora to learn that certain words just tend to appear in similar contexts. They place these words in proximate regions of a continuous vector space, right? Meaning in this paradigm emerges entirely from frequency and distribution. Aurora, however, proposes a strictly discrete logical paradigm. Here, meaning doesn't emerge from how often words appear together. Instead, it arises from the strict constraints required to preserve identity, allow exact reconstruction of phrases, and maintain logical compatibility across the entire system. It's a definitive shift from probability to structural logic.
Moving to Section 2, we'll look at the Aurora architecture hypothesis, specifically, meaning through constraints. The paper states this core hypothesis quite clearly. The meaning of a token emerges from the constraints necessary to preserve identity, reconstruction, and coherence within a recursive system of ternary tensors. Now, what makes this structurally significant is the mechanism of definition. A word obtains its internal representation not by mapping its proximity to other words. Rather, its tensor must mathematically evolve to ensure that all known linguistic and conceptual structures remain internally coherent. Meaning here is strictly defined by structural necessity rather than statistical approximation.
This brings us to Section 3, ternary tensors and identity, focusing on the mechanics of variables.
Unlike continuous vectors that rely on high-dimensional floating-point numbers, Aurora operates on just 3 discrete values. 0 represents absence or falsity. 1 represents presence or truth. But the critical architectural feature here is the value 2, which represents an unknown or unconsolidated state. The value 2 isn't just a void. It's an explicit, formal mathematical representation of uncertainty. The system is structurally prohibited from simply inventing a relationship when it lacks data. Instead, that unknown state is preserved until sufficient logical constraints allow for actual consolidation.
This explicit representation of ignorance leads to what the framework calls the rule of identity. The formula is f of x2 equals x. Basically, if x is our input and our knowledge base is in that unconsolidated state of 2, the output must exactly equal x. When the system doesn't know enough to transform the input, the output has to match the input precisely. This mathematical constraint establishes a strict baseline of stability. It prevents arbitrary transformations, what we commonly call hallucinations, and ensures that any modification to the output is strictly justified by logically consolidated knowledge.
Next is Section 4, recursive logic and consolidation, or the learning process.
A key architectural feature of this system is the principle of interchangeability. In classical systems, you have a rigid boundary between a token, the internal representation, and the external parameters or rules governing knowledge. Aurora collapses that boundary entirely. A token is simply partial knowledge, and a piece of knowledge is just a tensor that can be expressed as a token. So words, complete phrases, and logical rules all share the exact same logical tensor space. They only differ in their complexity and degree of consolidation, not in their fundamental nature.
To test this, the paper proposes a highly specific experimental protocol for consolidation. It starts by initializing the ternary tensors almost entirely with 2s, representing a state of maximum openness. Then, simple phrases are introduced iteratively, like fire burns or ice cools. The system applies the rule of identity, and as new coherent phrases enter the system, the tensors are incrementally adjusted. It operates much like a mathematical constraint solver. Each phrase acts as an equation, and the tokens are variables. The system only reduces those value 2s when absolutely necessary to preserve exact reconstruction across all observed phrases, effectively propagating meaning through recursive constraints.
Moving on to Section 5, we address semantic mitosis in polysemy, exploring the system's branching logic.
The framework handles multiple meanings by treating tokens as elastic nodes rather than rigid entities. For example, an initial token for the word bank begins in an open state, represented mathematically as 222. In classical embeddings, multiple meanings of bank might be compressed into a single average representation, which heavily relies on attention mechanisms to parse out context. In the Aurora architecture, the surface token merely acts as an access label. It points to a family of distinct, context-specific tensors.
The mechanism governing this branching is called logical tension. As new phrases are fed into the system, it measures the mathematical incompatibility between the new input and existing tensors. This tension is calculated based on three factors: direct semantic contradictions, the inability to reconstruct an input phrase, and the computational cost of altering already consolidated knowledge. If the tension is low, the existing tensor just adapts slightly. But if that tension reaches a critical mathematical threshold, a structural change is required.
When that critical logical tension is triggered, the system executes what the authors call semantic mitosis. Rather than averaging incompatible meanings and corrupting the tensor, the token simply bifurcates. Imagine the system has consolidated a tensor for bank relating to a park seat and is suddenly fed the phrase, "the bank offers credit." The logical tension spikes. But the system doesn't try to merge would and credit. It branches. It creates one tensor for the physical seat and an entirely new, unconsolidated tensor for the financial institution.
Crucially, this branching logic provides a highly robust defense against catastrophic forgetting. That's a known vulnerability in continuous neural networks, where new training can easily overwrite prior learning. By branching via mitosis, existing consolidated tensors are strictly protected from destructive updates. If the system learns about Mercury the planet and later encounters data about Mercury the liquid metal, it generates two distinct branches. The astronomical knowledge remains totally intact, completely isolated from the contradictory chemical data. So the knowledge base grows as a branching, crystalline structure, rather than a continuous, amorphous mass.
Finally, Section 6, System Advantages and Constraints, a theoretical assessment. The theoretical advantages of this architecture are grounded in efficiency and precision. Because the mathematics rely on discrete ternary states rather than massive matrices of continuous floating point numbers, the energy and computational costs for both training and inference should, theoretically, be significantly lower. Additionally, the explicit architectural encoding of ignorance, that state of 2, provides a structural guardrail against unjustified outputs. And because knowledge is updated via localized recursive constraint solving and mitosis, the system technically supports genuine incremental learning, avoiding the need for full model retraining.
However, we must also acknowledge the severe mathematical and computational risks outlined in the paper. The most pressing difficulty is the threat of a combinatorial explosion. If semantic mitosis is triggered too frequently, the sheer number of tensors will scale out of control. Furthermore, managing contradictions is highly complex. The system has to perfectly distinguish between a genuine logical contradiction and a mere contextual exception. To actually function at scale, the architecture requires an exceptionally rigorous formal definition of coherence. That is a non-trivial computer science problem, particularly when calculating the minimal coherent alteration required to update a tensor.
To conclude, the Aurora architecture presents a rigorous, alternative paradigm. It fundamentally challenges the assumption that intelligence is purely a function of statistical proximity scaled across massive datasets. Instead, it posits that meaning can be more efficiently and accurately captured through discrete, logically coherent constraints. The ultimate viability of this framework depends entirely on its ability to scale computationally without collapsing under combinatorial overload. So the critical question we are left with is this: will the definitive future of semantic representation remain anchored in statistical mass, or will it transition toward the recursive consolidation of logical coherence?